In this video, we will be discussing the concept of heat capacity, as well as doing some calculations related to it. In our previous discussions on thermodynamics, we had mentioned heat and work. One of the things that thermodynamics is very much interested in is the transfer of energy from one object to another. Now, you might have noticed that sometimes when you're heating things, different objects will increase their temperature at different rates. What we are interested in when we're talking about heat capacity is how easy it is, or difficult it is, to raise the temperature of an object by applying thermal energy in the form of heat, typically. So when a system absorbs heat, its temperature increases. The increase in temperature is directly proportional to the amount of heat absorbed. However, some objects will heat faster or to a greater extent with a given amount of heat applied. The proportionality constant between the raise in temperature and the amount of heat applied is called the heat capacity. When we're talking about an object, such as like a frying pan or something like that, an object that can't be subdivided, we use heat capacity, which is going to be represented with just a capital C. As we will see in a little bit, we also have the specific heat capacity and the molar heat capacity for objects that we can subdivide. But if we're talking about a physical object like a frying pan, you can't really cut a frying pan in half, and so you can't reduce the amount that you have. And so for objects, physical objects that can't be cut into smaller portions, we use the term heat capacity, and those heat capacities will have units of joules per degree Celsius or joules per Kelvin. Because when we're looking at our heat capacity, we're interested in the change in temperature, not the actual temperature, but the change. The difference between two different temperatures in Celsius is the same as the difference between two different temperatures in Kelvin. Because a difference in 1 degree Celsius is the same as the difference in 1 Kelvin, it doesn't really matter for your heat capacity whether you're calculating them in changes in Celsius or changes in Kelvin. But if you're trying to calculate the initial and final temperatures, you need to keep track of whether you're talking Kelvin or Celsius, just because you would have to do a conversion to go between Celsius and Kelvin. But so long as you're talking about the difference between two temperatures, it doesn't matter Celsius or Kelvin. The general equation is the amount of thermal energy transferred, or the heat energy, is equal to the heat capacity times the change in temperature. So we can look at this in a bunch of different ways. One could be how much heat is needed to raise the temperature of a particular object by like 2 degrees Celsius. So you're specifying the change in temperature, you're talking about the object and identifying its heat capacity and trying to figure out how much heat you need to apply. Or you could say, after applying 2 joules of heat to an object, what temperature should it be? And so that would be, you're looking to the change in temperature, you know your Q, and you know your heat capacity. Yet another one could be, you apply maybe 5 joules of heat, you notice that the temperature increases by 1 degree Celsius. What is the heat capacity? So you can be given any of these three, any two of the three, and ask for the third. The larger the heat capacity of an object being studied, the smaller the temperature rise will be for a given amount of heat. If the heat capacity value goes up and Q stays the same, then delta T has to go down. Now there's a bunch of different factors that affect heat capacity. The heat capacity of an object depends on how much you have. So if we were to try to heat 200 grams of water, it would take twice as much energy as it would to heat 100 grams of water. And you might have noticed this if you ever try to heat or boil some water. If you double the amount of water, it typically takes twice as long on the same setting on your stove that it would if you used half as much. The heat capacity also depends on what you are trying to heat up. So 1,000 joules of heat will raise the temperature of sand, of 100 grams of sand, by 12 degrees Celsius. However, that same 1,000 joules will only raise the temperature of 100 grams of water, the same mass of water, by only 2.4 degrees Celsius. Now, this is why if you're at the beach, the sand will feel a lot hotter than the water, and that's, well, because it is hotter, because the sun coming down will heat the sand up to a higher temperature because the heat capacity for the sand is less. So the temperature change from the amount of energy coming in will be greater for sand than it will be for water, which is why the water is cooler than the sand. Now, previously when we were talking about heat capacity, we were talking about for a particular object, like the example we used was a frying pan. For other things, we can actually subdivide it, and we're not talking about a physical object, but instead about things that we can subdivide. For example, water, or in the case of a frying pan, maybe the iron that the frying pan is made out of. We could use granules of iron and be interested in how much a particular mass of iron takes to heat up. So for things that can be subdivided, we're interested in the change in temperature that we observe for a given amount of energy for a given mass. The term that we will use for that is the specific heat capacity. The specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. We will denote it with a subscript of S. So we'll use the same symbol of a capital C as we did before with heat capacity, but this time the subscript S tells us that it is the specific heat capacity. The units are slightly different from heat capacity. In our previous discussion on heat capacity, the unit was joules per degree Celsius. This time it's joules per gram degree Celsius. And that's because when we were previously talking about heat capacity, we were talking about an object that could not be divided, it could not be subdivided. For this one, we can actually weigh out various amounts, and so we need to know how much we are working with. Similar to the specific heat capacity, we could also talk about the molar heat capacity. This is the amount of heat energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So the difference between the molar heat capacity and the specific heat capacity is essentially your molecular weight. For the specific heat capacity, it's per gram, and for the molar, it's per mole. If we look at a bunch of different values for specific heat, you'll see that there's a wide range in values, and water should stick out as being an anomaly. So most metals, like lead or gold, have fairly low heat capacities. What this means is a little bit of heat will cause a significant change in temperature. Water, on the other hand, is a bit of an outlier. It actually takes a large quantity of heat being supplied to water to get it to heat up. Similar to our previous discussion on regular heat capacity, or the heat capacity of a physical object, and being able to relate that to heat, when we're looking at the specific heat capacity, we can do a similar process. However, the equation is slightly different. We need to also include the mass. So the heat capacity of an object itself, or the specific heat capacity of an object, is proportional to its mass and the specific heat of the material. The more massive something is, the more energy it's going to take to heat it, and the higher the specific heat capacity for a particular material, the more energy you will need to put in to increase the temperature. We can calculate the quantity of heat that is absorbed by an object if we know the mass, the specific heat capacity, and the temperature change of the object. So this equation here looks very similar to the one we used before when we were talking about the heat capacity of an object, one that we could not subdivide. For this particular equation, we are looking at an object or a material that we can weigh out in various amounts. And we can tell that because we have this term here, which relates the amount of material that we're working with. So if something can be subdivided or can be weighed out in multiple different proportions, then we need to include an indication of how much material we're working with. So that would be the mass here. We then multiply it by the specific heat capacity and the change in temperature, and that will tell us the quantity of heat that was supplied. So now let's look at a problem dealing with our heat capacity. So we're interested in determining how much energy is required to heat a 5.00 gram cylinder of copper metal from 25 degrees Celsius to 100 degrees Celsius. So we're going to be using our specific heat capacity equation, which is our heat is equal to the mass times our specific heat capacity times our change in temperature. Anytime you're talking about a change in temperature, you're talking about the temperature final minus the temperature initial. So this would be equal to, we can plug in our values, 5.00 grams of copper times our specific heat capacity, which is 0.385 joules per gram degree Celsius. So our grams cancel out. We're now left with joules per degree Celsius. We can multiply this by our change in temperature. So this would be temperature final, which is 100 degrees Celsius, minus 25 degrees Celsius. This quantity here would be 75 degrees Celsius. If we plug this in to our calculator, you'll get 144.375 joules. Our Celsius here will cancel out our Celsius in here, or you could think about it as the Celsius here, canceling out our unit on our 75. In terms of significant figures, our mass has 3. Our heat capacity that is given, our specific heat capacity, has 3. Our temperature value has 2. So that means that our N value will only have 2 significant figures. So our Q will be equal to 140 joules of energy. So in order for us to heat a 5 gram cylinder of copper metal from 25 degrees Celsius to 100 degrees Celsius, will require 140 joules of energy. Water itself, as previously mentioned, has a very high heat capacity, 4.184 joules per gram per degree Celsius. This actually helps regulate the temperature of the planet. So because water can absorb a lot of heat energy without a large increase in temperature, that's due to its high heat capacity. This allows the planet to maintain a fairly even temperature. The planet is covered primarily with water. Without the water on the surface and without the water in the air, the Earth's temperature would be roughly the same as the moon. On the lunar surface, the side facing the sun has an average temperature of about 107 degrees Celsius. However, because the Earth has such a large quantity of water and water has such a high heat capacity, the side of the planet facing the sun is able to maintain a much lower temperature of roughly 20-ish degrees Celsius as opposed to 107, which is good for life on the planet. Also, because of the high heat capacity, water is commonly used as a coolant because it has the ability to absorb a lot of heat and remove it from important mechanical parts to keep them from overheating. Water can prevent the melting of these parts because it can be transferred from one location to another because it's a fluid. And so in engines, the coolant system that prevents your engine from overheating is primarily filled with water. They do have some antifreeze tucked in there to prevent the water from freezing in the winter. However, the coolant effect comes from water and the very high heat capacity that water has.